So yeah, this talk is going to be about vestigial order in multimode cavity QED. It's work I did with Yulia and Eugene, who are here. Actually did most of it when I was still here a couple of years ago. We're off by a sign error that I never could figure out. 2 years later, Yulia found a different sign error, and everything worked again, and so we could post the paper. Anyway, so this topic belongs in the sort of general genre of random buzzword in multimode cavity QED. You know what multimode cavity QED is, so it's incumbent on me to explain what random buzzword is. So these concepts of intertwined order and vestigial order and stuff like that come from the study of high-temperature superconductors and other strongly correlated materials. When you cool these materials down, what they want to do is a large number of different, semi-compatible things. They want to form superconductors, they want to form charge density waves, they want to become antiferromagnets, they sort of want it all. And so in order to describe what these systems actually do at low temperatures, you need to include a lot of different coupled order parameters. And this problem of coupled order parameters gets really interesting really fast. So for instance, you can take the simplest possible example, which is two coupled Ising order parameters. An Ising order parameter is something that's either positive or negative, that your spins are either up or down in the ferromagnet, and it's zero at high temperatures. So you might say, okay, I'm going to take two of these guys. Well, what can I get out of it? Well, there's four obvious things you can get out. And at high temperatures, nothing is ordered. Both order parameters zero. This is a paramagnet. At low temperatures, everything is ordered, so both these order parameters non-zero, and at intermediate temperatures, you might expect something in between. You have one order or the other. Well, so that seems like, okay, it's kind of boring, there's not very much going on, but it turns out it's not the complete story. And you can see it's not the complete story by realizing that you could also have set up your two order parameters in this way. I mean, you could have taken, instead of O1 and O2, you could have taken O1 and O1 times O2. These guys are local operators, so this guy's a local operator. It's a perfectly legitimate order parameter. In the fully ordered phase, it's, O1 is non-zero, O2 is non-zero, so O1, O2 is also non-zero. So this order parameter works just fine in the low temperature phase. It also works just fine in the high temperature phase because nothing is ordered. But if you look at the intermediate temperature possibilities, they're different. So this guy works the same in both representations, but these two phases sort of manifestly different phases. So in this guy, the product of O1 and O2 is non-zero, but O1 is zero, and presumably O2 is zero. Here, O1 is zero, O2 is non-zero. There's no reason for O1, O2 to be non-zero. So these are different possible intermediate temperature phases, and which one you see or which one you find in your description depends on how smart you were in picking your description. So these kinds of weird order parameters that are made up of sort of products and differences of products and exponentials and whatnot of the microscopic ordering tendencies, they're called various things. They're called vestigial orders, parasitic orders, various kinds of names like that. And the point is that if you weren't smart and you didn't put this order parameter into your theory to start with, you wouldn't necessarily realize that it was going to be there. And so you might say, well, okay, this is an interesting conceptual possibility. Is it ever realized? It turns out it's realized all the time in high-temperature superconductors. And so the simple way to think about this is in terms of the charge stripe. So these materials they like to form stripes, and the reason they like to form stripes is that you have, opposite points, opposite patches of the Fermi surface want to talk to each other. Okay, the details of that are not important, but what's important is that the wavelength of the stripe is set by some, continuously varying Fermi surface physics and has nothing at all to do with the wavelength of the underlying lattice. So these stripes are generically incommensurate, so they're not locked, they can't lock to the lattice. On the other hand, the orientational nature of the stripe, it's sort of sitting on a square lattice. So the stripe is either going up, down, or left, right. It's not going at a funny angle because the locking to the lattice prevents that. So it's orientationally locked, but sort of translationally unmoored. And if you take this to finite temperature in 2 dimensions, of course, what happens is that the stripe starts sort of wandering about, and you soon lose any sense of okay, this stripe is stripe number 5. It's sort of sitting at a particular position. Your translation order melts immediately, at least your algebraic order. On the other hand, the stripes still know they're going up, down, and not left, right. So that order, the orientational order, remains in place. And that's why orientation, the nematic, the orientationally but not translationally ordered phase that you get from looking at a stripe at low temperatures is a vestigially ordered phase, because the natural order parameter is this guy, which is like some kind of cosine, but the actual order that you see is the system has broken the up-down versus left-right symmetry, and that's fairly complicated to write in terms of these cosines. Okay, so that's how you get vestigial order in condensed matter systems. In this talk, I'm going to present sort of a very different approach to getting vestigial order, and the system that's involved is of course multimode Cavity QED. It's quite general, as I'll argue, in multimode cavities, but I'm going to focus on the two-mode case, both because it's just a lot simpler than the generic case, and also because there's this beautiful recent experimental realization of it by the ETH group. Okay, so Ben already talked about the self-organization transition, so I don't need to say very much about it. If you have two cavities, the atomic cloud is sitting in the waste of both cavities. You pump the system transversely in the sense that the laser is not pumping the cavities directly. If there are no atoms, the cavities would just be empty. The atoms scatter light between the pump laser and the two cavity modes. And at some point, if you crank up the pump, you find that it pays for the atoms to form a sort of grating and populate one or other or both of the cavity modes. So what they did was they looked at the phase diagram as you change the two detunings, the two cavities, and obviously if the cavity is less detuned, then it's more strongly coupled to the atoms, and so the less detuned cavity wins, and the system self-organizes into that, except along this high symmetry point where the two cavities were identical, and along this high symmetry point, what they found was that was sort of a U1 symmetry. Basically, the system self-organizes into some superposition of the two cavity modes. A superposition of two cavity modes is a legitimate cavity mode, so that shouldn't be too shocking that the system can do that. Obviously there's no vestigial order in this phase diagram, so what am I talking about? Well, they're sitting in a part of parameter space where you don't expect to see vestigial order, but as I'll argue, sort of a minor tweak to the experiment should reveal a new phase sort of sitting around this high symmetry line. To get there, we're going to have to get a little technical first, we're going to have to write down this Hamiltonian and try to solve it. As a sort of parenthetical note, why are we talking about a Hamiltonian? This is an open system, shouldn't be a master equation, stuff like that. Well, there are a lot of reasons why it turns out the steady state, the Dickey Hamiltonian, or in this case the multimode Dickey Hamiltonians, are close to their ground states, but for our purposes today there's much simpler reason, which is that for the most part today I'm going to be talking about instabilities of the uniform phase. And so the steady state is just no photons really in the cavity. The atoms are just sort of forming a uniform condensate, and I'm going to look at the excitation spectrum on top of that. And all these distributive processes do is they give me line widths, my excitations, and I can compute those if I want to. But this talk is going to be mostly about where the lines are, not how wide they are. I'll talk about how wide they are at the end. Okay, so here's your Hamiltonian atomic kinetic energy. It's the Bose-Einstein condensate. Maybe I should have made this linearly dispersing Goldstone mode. It doesn't matter. There's a potential in the z direction due to the standing wave pump. There's two cavity modes, and there's a process. These processes Ben talked about. At least this one he talked about, where the atom shuttles photons between the pump and the cavity. There's another process where the atom shuttles photons from one cavity mode to the other, or just sort of takes in a photon from one cavity and spits out a photon into the same cavity. And so those are the things that we're going to have to deal with. Okay, this is fairly messy. I mean, it's a many-body, non-linear, whatever. And so we want to make it something that's much more tractable. And to do that, what we're going to do is we're going to exploit the very nice, very simple structure of these interactions in momentum space. So instead of a normal many-body interacting problem where you need to keep track of every momentum mode, in these systems, a great simplification is you only need to keep track of certain special momentum modes that are coupled in. Okay, so let's build up momentum space. So I'm going to start out with all the atoms, the B, C. Then I have two cavity modes that I'm not keeping track of the cavity momenta at the moment. And so, okay, what else do I absolutely have to include? I absolutely have to include stuff that's coupled to zero momentum by the interaction terms. Well, okay, so first of all, there's the main interaction term where the atoms take a photon out of the pump and spew it into one or other of the cavity modes. So what that's going to do is so you start out at zero, you go up by the pump wave vector, and then you go in one of these four directions by dropping a photon into one of the two cavities. Okay, and so those are the four places that you can land up. Okay, and so you'll notice a slight difference from the standard single mode problem, those of you who are experts in that, which is that now because the angles, there's sort of a there's two places you can go, and they're not energy degenerate. One of them is slightly higher energy than the other. Okay, so that's in fact, and so okay, now that I have these guys, that these momentum states are in, I need to put in kinetic energy terms for these momentum states. That also needs to go in. At this point, I pretty much have everything I need to get the Dickey instability and a lot of the phases that people both at various institutions have seen over the years. But what I want to do now is I want to keep going. I want to put in stuff that that's due to the cavity-to-cavity scattering. And so, okay, what's going on here is that an atom starts out at momentum zero. It takes a photon out of one cavity and dumps it in a different cavity. And so it's easier to see there's sort of two ways to do that. Let's say you start out here, just for simplicity, you go down by dropping a photon into one cavity, cavity 1, and you can either go this way or that way by populating cavity 2. Okay? So you have these two momenta that, so the momentum difference between K1 plus and K2 minus, I'm going to call that chi, and I have this longer momentum difference that I'm going to call eta, and these momenta also they also belong in the description because they're coupled in directly from the condensate. Okay, so that's so I need to put in there kinetic energies. At this point, I'm going to use the fact that eta, the way I've drawn it, looks like a big number, so I'm going to pretend that it's unimportant, whereas chi is, in principle, a pretty small number. For instance, if the angle between the two cavities is small, so I can't get rid of it. So chi is the sort of new ingredient, needs to be there in a full theory of the two-mode transition. And so, okay, so once I've got K1 to K1, once I've got this guy and that guy and chi, I can see that I have a closed triangle, and so there's a couple of other terms that I can put in, but I mean, they've all got the same basic structure of being cubic terms in the fields that are left in the problem. So this guy, the original one I put in was cubic because it had one atomic field and two cavity fields. This guy it's the next order in the Bogoliubov expansion of the pump to cavity scattering process, but it's also there. Okay, so this is the problem that I'm going to have to try to deal with. It's a lot nicer than a field theory because it's just 5 modes and their reflections. On the other hand, that's still probably more than I, being a lazy theorist, want to have to handle. So what we're going to do is we're going to use the fact that you have a bunch of these linear terms, and so they're all coupled, and so they're sort of coupled linear oscillators, and I'm just going to find the normal modes and keep the lowest normal mode and throw out the other two. And that's pretty straightforward. It's a 3-mode problem. The two cavities are not coupled to each other, so I can do this separately for cavity 1 and cavity 2. Each cavity has the minus atomic excitation, the plus atomic excitation, the cavity excitation. So that's 3 modes, and so it's Bogoliubov because a dagger type terms are there, and so it's 6. It's a 6 by 6 matrix. I can diagonalize it, and so I end up with basically 3 normal modes. And we sort of understand where these come from. So if you look at the problem, if you look at this far end of the diagram, where there's no pump, well, there's three modes. There's one mode that starts out at the cavity detuning from the laser. As Ben said, the cavity is slightly blue with respect to the laser, and that mode is like at about a few megahertz up. Then you have one mode that starts out, you have two modes that start out as atomic excitations, and those start out at recoil. Recoil times a half and recoil times 1.1 or whatever. Like they're basically at the recoil scale. And then now you diagonalize this 3 by 3 matrix. You sort of understand what's going on. Like one of them, the higher mode goes up, the lower mode goes down, the middle mode doesn't do very much of anything. At some point, in fact, the lowest mode crosses zero, and this is a conventional self-organization transition. So I'm going to say that we're pumping the system hard enough that this guy is well separated energetically from that guy, and I'm going to project my problem onto three oscillator modes. One of them is this lowest atomic polariton. Polariton's just a buzzword. It's like it's like an atom coupled to a photon. It's a density wave coupled to a photon, and I'm going to throw out the other two. And so that leaves me with sort of a fairly simple problem with three oscillators. One of them is the first atomic mode, its lowest polariton. Then I've got the other. So each Dickey type problem has lowest polariton that's about to go soft. And there's two modes. There's two of these polaritons, and there's this chi mode, which corresponds to the momentum difference between the two polariton modes. And so, okay, I'm going to write down the Hamiltonian that includes these three guys, and so it's got the usual quadratic pieces. It's got a quartic coupling that's basically due to number conservation, and it has this cubic coupling between mode 1, mode 2, and mode chi. And this is what the process where you take a photon from mode 1, dump it in mode 2, and create a chi excitation looks like once it's been projected all the way down to this low energy subspace. Now, if I threw out the chi mode for whatever reason, let's say, as in the ETH experiment, that it's not actually at particularly small momenta, it's at a big enough momentum that it's like totally irrelevant to low energy physics, then I'd end up with this very nice, simple two-coupled nonlinear oscillator problem, and this would give me the U1 symmetry and all the physics that ETH have already experimentally seen. But what I care about is what happens when I can't get rid of the chi mode, because this difference mode is at low energies. And so what I'm going to argue is that under certain conditions, this guy actually organizes before the other two, before the actual self-organization transition has happened. Why is that? Let's again think about this in terms of an energy level diagram. So I haven't started pumping the system yet. This is how my modes are organized. I'm going to say that for whatever reason, the energy... Right, so let's start simple and say the momentum difference between K1 and K2 is small, so the difference mode is at a very small momentum, and therefore it's a very small energy. It just doesn't cost... It's a very long wavelength fluctuation. So if I make that assumption, then I start out, well, this guy is at pretty low energy, then I have... at a small fraction of recoil, these two modes of the old atomic polaritons, they start out at the recoil. There's the cavity polariton that starts out at the detuning, and of course the states, with two polaritons or a polariton of one kind, a polariton of a different kind, all those many body states are sort of floating around in my Hilbert space. But this is the one that actually matters. And this is the two polariton state with one polariton in mode 1, one polariton in mode 2. Okay, now I start cranking up the interaction. I already talked about this. The cavity-like mode repels the atomic type mode, and so this guy is going to start going soft. It's lowest polariton I care about. As I keep going, though, okay, and so the key point here is that as this guy softens, then so does a state with two polaritons, because a two polariton state has an energy that's twice the energy of a single polariton state. Okay, so now I start softening these further, and I realize that because this cubic nonlinearity, what the cubic nonlinearity does is it couples chi to the two polariton sector, because it can kill a chi and create excitations in mode 1 and mode 2 simultaneously. That's what the cubic term allows you to do. And so if this guy gets pushed down faster than those guys come down, then this guy goes through 0 and the system organizes in the chi mode. Well, why would that happen? You know, it looks like a higher order process. It is, but this guy starts out a lot softer than the others, so it has less room to go down before it hits 0 and orders. So that's the basic physics of this phase. Well, what happens? Okay, so the vestigial ordered phase is what happens when the chi mode softens first. So what happens when the chi mode softens first? Well, first of all, of course, you have a density wave in that mode, because that's what it means for the mode to soften. On the other hand, that density wave doesn't directly cause superradiance because the chi mode isn't linearly coupled to any photon mode, and instead it's quadratically coupled. So what it ends up doing, you can just figure out straightforwardly. You just plug in, just say the chi mode has an expectation value, and now you have a simple problem of coupled oscillators. And what it does is it breaks the sort of rotation symmetry in the two mode sectors. If I started out with two degenerate cavity modes, what I'd find is the symmetric combination, the antisymmetric combination of the two cavity modes would be at the same energy. There's nothing mixing them, so they're all degenerate. Any linear combination in that space would be degenerate. But what happens now is that this guy, this expectation value allows me to mix the two modes, and so it pulls down the symmetric or the antisymmetric combination. It pushes up the other combination, and so what started out as two degenerate modes become sort of two non-degenerate modes, and so that's spectroscopically visible. Yeah, and you can just sort of see that by looking at the transmission spectrum of the cavity. It's also pretty straightforward. Just look at this in terms of like just time of flighting the atoms, and so you're going to see you're either going to see a density wave or you're not, and that's your order parameter. Okay, but you can see why it's a vestigially ordered phase, because what happens is that neither mode 1 nor mode 2 organizes, but the product of mode 1 and mode 2 develops an expectation value because this guy has an expectation value. Okay, so this is all just perturbative theory, but we also tried using a variational state, a pretty general variational state with both coherent states and squeezing to try and capture this, and two-mode squeezing, try and capture the vestigially ordered state, and you'll see that this is what you get to the phase diagram. Sorry, I should have labeled it better. So this guy, as you go to the left, you're going to low temperatures, the strong couplings are above threshold. So you're up here, mode 2 is in play, mode 1 is not in play, so you just superradiate into mode 2. You're down here, the opposite thing happens. Mode 1 is in play, mode 2 is not in play. You, one or the other. Like I can't remember which one's 1, which one's 2. But if they're approximately symmetric, then what happens is you hit this. You have two transitions. You first form vestigial order, and then as you keep going, you finally end up in a phase where both modes 1 and 2 are self-organized. So you have this intermediate temperature phase that's vestigially ordered. Something that's sort of interesting is that you don't, if you just do a mean field theory, and a mean field theory in our variational terms means that you make the ansatz that the wave function is a coherent state of the modes, then you don't see this at all. You need squeezing between mode 1 and mode 2 in order to see vestigially ordered phase. Okay, and so that might have other implications than condensed matter as just a good way of variationally looking for vestigially ordered phases, but I don't want to talk about that now. Okay. Finally, you can play around nonlinearity. So what conditions favor the vestigial order phase? Basically, what you want is the chi mode, you want the sort of difference of two memento mode to start out as low energy as possible. If it doesn't start out at particularly low energy, then what ends up happening is that you get this alternative phase diagram where you have a tetracritical point So up here you're organizing to mode 1, down here you're organizing into mode 2. Here you have this sort of little fan where you're organizing into both modes. And so interestingly, the numerics here isn't stable, so there might be a first order transition. There might be a first order transition between these two phases, which might be the true ground state. Okay, that's most of what I wanted to say. Right, let me. Oh yeah, that's right. I need to talk about multimode cases. So fine. So I said most of this already. What a sufficiently soft chi mode. You plug in realistic numbers, which are pulled out of the ETH experimental paper. You find that what you really want is for the sort of the energy of the mode at the difference of the two cavity momenta to be less than 30 hertz, and that also translates into a time scale that's sort of the most optimistic time scale for this instability, which is about 100 milliseconds. Like that's about as good as you can do with those parameters in two cavity modes. I should say, did I put this in? I guess I forgot. So you know why? Okay, so did I? Right. So I should talk a little about how you actually get the chi mode to soften. So one way to do it, of course, is to say I'm going to have the angle between these two cavities to be like 2 degrees. Now that's not a particularly sensible thing to do experimentally because you have sort of obvious issues with optical axis. But it turns out you don't need to do that. What you can do instead is you can notice that these guys, the two cavity modes and therefore their associated polaritons, have both an x momentum and a z momentum, whereas the chi mode only has a momentum along the z direction. So if you just if you kill the momentum along the z direction by applying a strong lattice of any periodicity along the z direction, you're golden because now you can create whatever momentum excitation you want. It's not going to cost you any energy at all. So actually getting the chi mode to soften is not a problem. The thing that is potentially a problem is, for the two-mode case, is that these timescales are not particularly great. I mean, you might just lose your vestigial order before you're really able to do anything with it. Okay, so that's two modes, and you know, two-mode cavities are great, but like we really care about them as sort of toy examples of multi-mode cavities. So how does this scale up? In fact, it scales up quite nicely because what you're doing here is you're sort of creating a long wavelength excitation that corresponds to the difference between the wavelengths of two sort of the difference between the momenta of two short wavelength excitations. And so in a multi-mode cavity, you know, you have a bunch of different states, and they're all sort of individually fairly sort of rapidly oscillating. But if you go from one state to the next and you look at the momentum difference between them, it's a small momentum difference. You can mix two adjacent modes with a long wavelength fluctuation because you don't need to change m and n, you know, whatever numbers you care about, by 1. So this is a long wavelength fluctuation, and it can actually mix the same long wavelength fluctuation. In many cases, can mix a large number of pairs of cavity modes, and so you actually get a factor of n enhancement where you have n cavity modes in the system. I mean, the calculations become a lot hairier because now you're dealing with Hermite Gaussians instead of momentum states, but so that's the basic picture. And in fact, this even goes on to so you can think about this. A nice limit I like to think about is that of a photonic band gap crystal. So, so this is, let's say, the p-type band of one of these crystals, and so you know, by sort of the same logic as the Cavity QED self-organization transition, the system sort of wants to self-organize out here, but this is a large momentum state, and instead what the system can do is it can sort of pull down some combination of all of these modes lying near the bottom of the band, and so it can do that, and at the same time the atoms can sort of form a long wavelength modulation. So I mean, okay, if you work through the details of this, what's actually going on is that the atoms are sort of self-trapping, and when they self-trap, they're sort of forming a not completely soft but somewhat soft combination of all the modes near the bottom of the band. They're sort of pulling them down, and so there's sort of a localized mode where the atoms are, and the atoms form a sort of localized wave packet. So that's what vestigial order looks like in one particularly simple limit if you have a large number of modes in play. All right, so that's most of what I wanted to talk about. And so to summarize, you have this new phase, which we've been playing around multimode cavities for a long time, and we never thought it was going to be there. We never really thought about it, and it turns out it is there, and it should be looked for. The fairly straightforward diagnostics, and it seems to scale well to the case of many pairs of modes. Okay, so Dan wanted an adventurous outlook, and from my point of view, there's sort of a number of ways of thinking about what Cavity QED, and especially multimode Cavity QED, has to offer condensed matter physics. So one of them is, here's an example where you have a very stripped down version of a phenomenon that happens all the time in condensed matter. But in condensed matter, it's sort of a complicated phenomenon involving, Merman-Wagner theorems and long wavelength fluctuations and all that. Whereas here it's just a very simple few-mode problem, which you can really work through and understand in a great level of detail. So that's in some sense a thing that Cavity QED has to offer condensed matter. And there's sort of, I'd say, much more general questions where, again, Cavity QED and these infinite range interactions are useful. One of them is this question of how systems approach thermal equilibrium and how, entanglement and information spreads in many body systems. And so these are systems that are, in some sense, long range in real space, so they're very different from the systems that people normally look at in condensed matter. But one thing that's sort of special about them is they're very, very structured in momentum space. So you start out with a condensate at momentum 0, and you just sort of move up these ladders. And so if you think about sort of, if you think about a quench type experiment, you start out with uniform condensate, and you let it go. It's going to spread out in momentum space in some deterministic way. And you can talk about things like entanglement spread in momentum space, how an operator spreads out in momentum space. All the questions that you think about in the conventional systems, you think about these as real space questions, but here you can think about them in much more general contexts. And for instance, you can add in short and long range interactions. You can sort of see how the real momentum space, information spread sort of tie in with each other and ask various questions like that. So I mean, this talk is about equilibrium, zero temperature phases in some sense, but really it was about instabilities of an open system. But there's also sort of a world of questions out there about how non-equilibrium dynamics works in Cavity QED that I think people haven't really touched so far. So that's my outlook, and amazingly, I think I'm kind of on time. Thank you. That's one way to do it.
In the Esslinger setup.
Yeah.
Because the angle is fairly substantial.
Mm-hmm.
Now, for Ben's experiment, the angle's pretty small.
Mm-hmm.
So does he need to add a lattice as well, or does he?
I don't think he needs to do anything.
He just needs to look.
Yeah.
What are you doing here? Here.
Yeah. Yes. Yeah.
From the point of view of, if I have like two modes of a cavity, I can sort of think about it as a single mode of a more complicated cavity. And there are sort of symmetric and anti-symmetric versions of that. And then I might put in an atom and consider it as a dispersive coupling, which will break the symmetry between those two modes. But I guess nothing that in that picture has anything to do with photon-photon correlations. It's just, I can then populate them with whatever quantum state I like. So
yeah, that's right.
I can believe you get like two modes squeezing emerging from that problem. I guess the question I wanted to ask is it an emergent thing like that, or is it sort of required in order to get the pattern formation?
Right, so let me try and rephrase that in my language. So if I have a uniform atomic distribution, which is what I put in, okay, and the atoms aren't doing anything, then there's a symmetry that says that mode 1 and mode 2 are not coupled. There's no medium in there. There's no matrix element for the uniform atomic distribution. In order to get this matrix element, I need to spontaneously break a symmetry. And once I spontaneously break a symmetry, I now have a symmetric and antisymmetric combination of modes that are no longer, they used to be degenerate. They used to be guaranteed to be degenerate and have no correlation, just not talk to each other. Now once the atoms do develop this modulation, then they behave like the medium you're talking about. They're allowed to couple the symmetric and antisymmetric modes and split them. But that correlation only emerges after, or it emerges concomitantly with the atomic ordering. It can't just happen on its own.
So I guess my question was, do you always see two modes squeezing of the photon field between the two different modes?
You should. I mean, I don't see, I mean, in this phase, I don't see how you get around it. I mean, obviously, you might also see it. So if you go to the, let's imagine going further down to the phase, right, so where I start out is I start out with a guaranteed degeneracy where the two modes just not talking to each other, A dagger 1, A1, and A dagger 2, A2, and you know, yeah, sorry, A dagger 1, A1, and A dagger 2, A2 are sort of things that have expectation values, but any cross correlation is guaranteed to be 0. Now I have the vestigial order phase. I go into it, and now what happens is that once chi orders, A1, A2 is now allowed to have an expectation value. But A1 and A2 separately are still not, they're still 0. And now I go into the fully ordered phase where A1 and A2 are both ordered. And once that happens, what I'm going to have is I'm going to have a coherent state in A1, a coherent state in A2. I'm also going to have some squeezing probably on top of that, but it's going to be a small effect. Whereas in this phase, the squeezing is the only effect.
So if I look at photon coincidence
Yes.
on the outputs
Yeah.
from two different modes, you'd
Yeah.
expect to see a
Correct.
constant signal.
Yes.
So how should I understand the microscopic process here? So two pump photons come in and they split as a pair into the two cavities.
Yeah.
And I guess the symmetry breaking that chooses the plus or the minus, you're saying, is some long wavelength modulation within the gases if you
Exactly.
have like a periodically poled medium.
Yeah, and it can sort of periodically sort of the sort of two periodic patterns, which is sort of one pattern and its reflection, and those give you, one of them pushes symmetric down, the other one pushes the antisymmetric down.
And then, like with parametric oscillators that are below their threshold, you expect before it lasers, it'll start squeezing.
Yeah. I think that's right. I mean, so in many of those cases, you're actually allowed. There's nothing. So one mode, squeezing of the A1 dagger A1 type always exists below threshold for the Dickey problem. The thing that's special about here is the cross squeezing, and that requires the atomic ordering. So that's I think so that just sort of, it doesn't sort of smoothly onset. It's not there at some point. It's just there. That's an order parameter for the transition.
Just to follow that up, my understanding is that non-degenerate parametric amplifiers can have this sort of the same sort of order parameter that you have squeezing the correlation between two modes. So, but there's no atomic medium. It's just a non-linear medium that's coupling two different oscillators.
Yeah.
What's special about the atomic medium ordering?
It's the symmetry breaking aspect of things, right? So in that case, the sort of two mode squeezing term you're talking about isn't forbidden at sort of weak coupling by any symmetry. It starts out small and non-zero and becomes big and non-zero. Whereas here, the symmetry of the symmetry of the problem, the fact that the atoms are sort of symmetric over this translation guarantees that cross correlation term is 0. It's not, I guess, the point is it's not sort of small and then big. It's guaranteed to be 0 and then it turns on. And that's different from, I think, the cases you're talking about. Yeah.
Maybe a bit technical. Here we have this nonlinear Hamiltonian.
Yeah.
You calculated the spectrum.
Yeah.
This you did by truncating some of the Hilbert space?
Yeah, so the Hilbert space is, it's sort of, right, so we did it in two ways, right? The first is just perturbation theory, where you have this problem of three coupled oscillators and you just perturbatively construct the eigenstates of the problem, right? And so that's, because it's a bunch of coupled oscillators, you can just do that in the sort of standard many-body perturbation theory for a few modes. The other thing we did was this variational thing, where we put in this ansatz and variationally minimized the energy. And so those two things agree in terms of what they predict. But it's, this guy is not, it's not truncated, it's just an ansatz, and so it cuts down your sort of complicated problem to a problem of finding like 6 parameters or like 9 parameters or something.
With this answer, does it report you that in the end that the population in this chi mode tends to infinity?
It doesn't, because there's quartic nonlinearities that cut it off. So it's, eventually there's a certain number of atoms of problem, and so eventually that gets cut off by higher order stuff. But it grows and it sort of saturates somewhere. The question from back somewhere? Or? Yeah.
In a system of finite size,
yeah.
chi mode exhibits a length scale that may exceed the size UVC.
That's.
How does that come into play?
Right, so that's a really interesting question. So I'm always assuming here that the BEC is big enough, the chi mode is not, that the chi mode is a finite momentum looking mode. If it turns out to be like the overall like symmetric, if it turns out to be the lowest mode in the oscillator, then I think you have a problem, because I think in that case you can start populating it like even at very weak coupling. Yeah, you've explicitly broken that symmetry, because you're sort of saying, because as Jan, I think, implies, you sort of, you pick that rather than like that or that, and so like, you've explicitly broken the symmetry, and so that's right. Yeah. But I mean, again, in my proposal for the Estinger setup, the chi mode is actually at low energy, but it's not at low momentum. It's at big momentum. It just happens to have momentum along a direction where there's where the energy doesn't depend strongly on momentum. The mass is big.
I mean, it'll be like the images vector.
Yeah.
You place the atoms somewhere,
exactly.
and you select the cavity
Yeah.
as a coupling between
Yeah.
previous cavity. All right.
Right.
Great. We'll
Thank
end
you.
here. Coffee break time.